Hello everyone, my name is Ro'i from the Technion, and thank you for attending my talk. Today, I will present our paper, Queuing Inference for Process Performance Analysis with Missing Lifecycle Data. This paper is a product of a joint work with Guy and Avi, which are also from the Technion, Arik from the University of Toronto, and Matthias from Humboldt University of Berlin. This is the outline for my talk, beginning with the motivation for this talk, followed by our methodology, results, and concluding remarks. As a way of motivation, consider, for example, the following hospital. In this hospital, patients can go through 3 treatment steps: vitals, consultancy, and imaging. This hospital has a system of queues which also provides a process that defines that vitals, if conducted, happens before consultancy and imaging. Yet, some patients arrive directly to these treatment steps, and in addition, all these steps are also recorded in an event log. The event log contains the start and completion events of each of the activities, as well as the time it occurred and the resource who conducted it. For example, looking at the vitals activity, we see 4 corresponding events in the log. Both case ID 11 and 13 went through the vital step, for which the start and completion events are recorded in the log. As a final note, there are 2 types of arrivals into the system, namely external and internal. For example, the vital step can only have external arrivals, while imaging, for example, can have both external arrivals and internal arrivals. For the internal arrivals, we assume that the transition times are negligible. For example, once the patient number 11 completed the vital step, she directly arrives at the imaging step. Looking at each of these steps, this is our view of the queuing activity lifecycle. Looking at a single activity, we consider 3 lifecycle states: arrival, start, and completion. The start and completion events are known, since the resource who conducted the activity reports them. Yet, the time at which the patient has arrived at the system is usually not recorded. In what follows, when patients arrive externally, otherwise we can infer their arrival time is missing. This, in turn, withholds our ability to provide the patient with the queue length and the waiting time. In this work, we focus on predicting process performance indicators with missing lifecycle data. Specifically, we are interested in the following questions: what is the queue length in a given timestamp? And what is the waiting time for a customer who enters the queue? These are 2 very important questions, which are crucial for locating bottlenecks and understanding system dynamics. In terms of related work, the first attempt to combine queuing theory and the statistical approach was done by Larson in 1990. He coined the term queuing inference engine for a set of techniques that try to reconstruct performance measures such as queue length and waiting times from data. Larson's approach and those who followed make multiple assumptions regarding the distribution of the data, for example, Poisson arrivals. The work by Berti-Simas made the approach more efficient in terms of computation, and Mendelbaum and Zeltine proposed an extension of the QIE for networks of queues. Another related work is done by Mike Jordan and Chris Sutton, who proposed the Bayesian inference approach to estimating queuing parameters under missing data. Lastly, in process mining, the approach by Senderovich et al. Reconstructs queues when various information about the log is available. However, they do not handle the case that the arrival into the system is unknown. We now move to our proposed methodology. We begin with some assumptions. First, we assume that the server is always busy. This means that in case that there is a patient waiting for service and there is a server available, she immediately starts the service. Second, we assume that there is a one-to-one correspondence between an activity and the resource. Finally, as stated before, we assume that the external arrivals into the system are missing. Now, I will present an overview of our framework. The main input for our framework is an event log. Out of the event log, we generate two sets of features. First, we utilize a queuing inference engine, QIE, to generate a queue length distribution, out of which we create a first set of features. In addition, we directly use the event log to gather some log-based features. Then, combining the features to create our suggested feature representation. This feature set is then used to provide predictions for the aforementioned process performance indicators, namely the queue length and the waiting time. One of the main components in our feature extraction is the QIE, Queuing Inference Engine. A QIE is a statistical method based on hidden Markov models that provides performance estimation under missing data. In this work, we use a QIE to construct a distribution of the queue length. Using QIE comes with an additional set of assumptions. Specifically, it assumes Poisson arrivals, a first-come, first-served policy, and non-idling resources. All these assumptions rarely exist in real-world scenarios, and theoretical benefits are usually analyzed in sterile scenarios such as the one of MM1 queuing systems. Yet, as we show in our empirical evaluation, using a QIE to generate features to be used in a supervised learning fashion, as we propose in this work, is also provides accurate predictions, even when it comes to real-world data. After briefly describing the QIE, we now turn our efforts to the feature extraction. Having an input event log, we first use a QIE to generate a queue length distribution. Since one cannot simply feed the distribution as a feature representation, we offer the following set of features. We divide these features into three groups. The first includes features that capture the central tendency of the distribution. Specifically, we use the mean, median, and mode of the distribution. Note that the QIE enables us to obtain the exact theoretical queue length distribution conditioned on the event log. Under the aforementioned assumptions, theoretically, the mean may serve as a prediction for the queue length, as the expected value is known to be the best least squared predictor of the value itself. Then, aiming to discretize the distribution, we use its quantiles as features. Specifically, in this work, we use the deciles of the distribution. Finally, we aim to capture the distribution dispersion. We use the moments of the distribution. Specifically, we use the second, standard deviation, the third, skewness, and the fourth, kurtosis. in addition to the QIE-based features, we directly use the log to generate a few process-aware features. In this work, we use the elapsed time, the case number, and when exists, the type of the patient, and the delay between the scheduled appointment and the actual appointment. Having the full feature set, we now turn our efforts to the prediction of the queue length and waiting times. We first aim to predict the queue length. To do so, we cast our problem as a regression problem, aiming to find a regressor that predicts the queue length. To implement this regressor, we use an out-of-the-box approach, experimenting with several types of regression models, including linear regression and gradient boosting. Similar to the queue length prediction, we also cast the waiting time estimation as a regression problem. We explore two alternatives for this regressor. The first uses the predicted queue length as a single feature. Under the relevant queuing assumptions, one can directly express the waiting time as a linear function of the queue length. As a second alternative, we simply use the same feature set as the one used to predict the queue length. We now move to the highlights of our empirical evaluation. We used two data sets in our experiments. The first represents sterile data simulated based on an MM1 queuing system simulator. The second is based on real-world data coming from a large outpatient hospital in Boston, USA. We begin with the queue length prediction, comparing three evaluation measures, namely the RMSE, MAE, and MARE. First, we see that the gradient boosting outperforms linear regression, probably due its ability to capture non-linear relationships between the features. For the MM1 dataset, which presents a sterile setting, the mean of the distribution should suffice to achieve the best prediction of the queue length. While it holds for MAE and MARE, we see that our method provides a slight improvement in RMSE. For the DFCI dataset, the suggested full set of features provides the best prediction. This demonstrates the effectiveness of our approach in real-world scenarios, especially when additional features are available. Similar observations can be seen for the waiting time prediction. Of the MM1 dataset, the baseline provides slightly better RMSE, while the distribution-based model achieves the best MAE and MARE. For the DFCI, our suggested model provides the best prediction. We now provide an anecdotal analysis. The shaded area in the figures represents the distribution. The figure also presents the predictions using the distribution-based features only in red, and using the full sets of features in blue. For the MM1 dataset, we can see that both of the models yield similar results, with the ability to rise and fall with the actual behavior of the instance, yet not venturing far away from the center of the shaded area. A different picture is revealed for the real-world data. While the instance remains mainly within the distribution shaded area, we observed a deviation at the beginning of the tested interval, which likely due to evaluation of the arrival time assumptions. Initially, patients likely arrived in a bulk rather than according to the Poisson process as the QIE assumes. As we can see here, the full model yields the best performance. The prediction of the waiting times shows a similar pattern. For the MM1 dataset, both models exhibit a similar behavior rising and falling with the actual waiting times. For the real-world data, using the full feature set yields a more agile model that identifies better changes of the actual waiting times. As a final analysis, we look at the most dominant features for each dataset and predictor. Overall, as expected, for the MM1 dataset, The distribution mean is the most dominant features for the Q-length prediction. For the waiting time prediction, the dispersion features, and especially the standard deviation, are dominant. For the DFCI dataset, features such as the delay and elapsed times influence both predictions. The upper quantiles, Q9 and Q8, are also influential, capturing the right tail of the distribution. We now conclude the presentation. In this work, we provide a methodology to estimate two important performance indicators, namely waiting times and queue length over incomplete data. We further offer a novel use of the QIE to generate features from an event log, which can be used in a supervised learning method. Thank you very much for your attention. And if you have any questions, feel free to ask or virtual approach me or one of the other authors. Thank you very much and have a nice day.